Okay, today is the 23rd. And we are going to look at the quantum mechanics of multi-electron atoms. We're going to get what are called atomic terms and states, going considerably beyond, I might add, what our book does. So we'll start with where our book is, then we'll build considerably beyond that and come up with a wonderful basis for understanding the structure of atoms, which we'll then extend to the structure of molecules in a very nice and cohesive way. So what we want to do is look at many electron atoms. Within the so-called orbital approximation. And the idea of the orbital approximation is treat electron repulsion on average. We're not going to try to account for every last repulsion with the repulsion. Remember, those cross terms made Schrodinger's equation impossible to solve analytically because of all the so we're going to treat it on average. We're going to make the orbital approximation. So let's take an isolated atom of carbon. What we would have in carbon, our neutral carbon, we have 6 electrons, and each electron goes into an orbital. So our total wave function is a product of one electron wave functions. Or orbitals. So we have a total wave function R1, R2, R3, R4, R5, R6. These are the coordinate vectors of the 6 electrons in carbon. And we will approximate that in the form of atomic wave functions. Now, we'll write N, L, M sub L, S, M sub S of R1. And now let's take a moment and figure out what this is. This is a 1s with the spin up. That's what that means. So the N quantum number is what? 1. The L quantum number for an s orbital is always 0. And if L is 0, what's M sub L?
0.
0. S is always 1/2. Up arrow means it's plus 1/2. So we have 5 quantum numbers, 1, 0, 0, 1/2, 1/2. And that's the same as writing 1s up. Then the next one is going to be psi of R2. And it's going to have the quantum numbers, and we'll just write them without it'll be 1, 0, 0, 1/2, and then there's a difference. Minus 1/2 for that one, that's right. And this gives us 1s down. Okay. And then what's the next thing we write in electron configuration? Well, isn't it the 2s? 1s,
2s.
then 2s, and then 2p. So this is going to be the 2s with spin up. Third electron, and it's going to be 2, 0, 0.
Did you say minus 1/2? Sorry.
Minus 1/2 is spin down,
Spin
plus
down.
1/2 is spin up.
Gotcha. Okay.
Thank you for asking. Okay, 2s's, we just jacked the principal quantum number up by 1. So it's 2, 0, 0, 1/2, 1/2. And for R4, this is 2s with the spin down. So this is 2, 0, 0, 1/2, minus 1/2, just like 1s, right?
Mm-hmm.
Now, this gets really interesting. Now we're going to get some very intriguing results here. So these are going to be 2 P's. And there can be many, many choices on these. In the S's, there wasn't much choice at all. R5 and R6. So we know our principal quantum number is 2. What's our L quantum number?
1.
1. And what values can our M sub L quantum number take on?
Halves.
Uh,
I don't know.
M sub L goes between 1 and minus 1 in this case, or in general between L and minus L. So we can have multiple values. We can have 2, 1, 0, or minus 1. So we might want to say that. We'll put a little box around. Multiple values.
That's for M sub L, right? Okay, yeah.
For M sub L. Oh, wait a minute. I'm off one. It's 1 for L and multiple values for M sub L. The S quantum number is always 1/2. Then we can have the values either plus 1/2 or minus 1/2. And we have the same problem over here. So in other words, for carbon, there's not just one simple, well-defined choice. There are a bunch of different ways we could put the electrons in with different values of M sub L and different values of M sub S. There are a whole bunch of different ways it can be done. Okay? Now, what shorthand notation have we learned for all of this? This taken together is just 1s2, right? These two taken together are 2s2. And without specifying all the details, this is just 2p2. So you can see how close what you've been writing all your life in chemistry is to this orbital approximation where we have these wave functions. And interestingly enough, these are the same way for the 1s and the 2s, the exact same wave function except for the spin of the electron. So writing 1s squared makes a lot of sense. Or 2s squared makes a lot of sense. It's the 2 p's where we have the challenge.
You have exactly what I had.
Oh, it's awful.
It stays in your chest for a little after the sickness.
Yeah, I'm just knocking all the slime out of there.
Yep. That's what I had.
That was just awful, terrible. Now, we introduce a new quantum principle, at least in this course. You've worked with and seen reference made to the Pauli principle. In an atom, every electron has a unique address. Electrons are fermions, which means that 2 electrons can't be in the same place at the same time exactly. So each electron has a unique set of quantum numbers in the atom. And in our example of carbon, we provided that. So electron 5 and electron 6 can't have all the same quantum numbers. And we'll see how that works in just a moment. So, one of the things we should realize in these multi-electron systems is the following. Let me choose, this marker works. The 1s orbitals and the 2s orbitals of carbon are, within themselves, they're completely closed. The spins are paired, and if the spins are paired, it means that the spin angular momentum of one electron cancels out the spin angular momentum of the other. That's what we mean by paired spins. Their spins cancel out. So if you bring $100 in the casino, you play poker, and let's see, is that a good analogy?
Sounded good at the start.
Let's go to Vegas and do it, right? I've got a conference in Vegas this weekend, so I'm going to Vegas. If you'll give me $100, I'll give you 50% of the earnings.
Ooh.
I mean, if I'm throwing hot rolled craps, man, I could make a fortune. I mean, consider this as an investment. Dr. Kenny takes crap rolls for his students. Yes, wow. No. So the idea is the spins that cancel out, their angular momentum cancel. There's no net angular momentum arising from the s orbitals, either orbitally or spin-wise. So in one sense, this part of the molecule is transparent. There's no net angular momentum emanating from these 4 electrons or the orbitals, orbitally or spin-wise. There's no angular momentum. However, there's a host of possibilities with the partially filled P shell. And we want to look at those possibilities.
Does that mean we always ignore the s orbital?
Unless we break electrons out, there's no net spin angular momentum or orbital angular momentum, so they don't really contribute any angular momentum to the problem.
Okay.
That's why we're neglecting them. You know, it's like history majors. What do they contribute to society? For politicians, you know, they don't have any angular momentum. I am teasing. I mean, at least the garbage man is doing noble work. He's eliminating the amount of crap in the world, you know, taking it to the dump.
That's why I wanted to be an us, it'll be a garbage man.
Yeah, I mean, why not? You get to drive a big truck.
I get to
you know,
ride on the back.
Right on the back, yeah, exactly. Yeah, I totally get your reasoning. Okay, so. So how many p orbitals are there? There are 3 with m sub l values of -1, 0, and 1. Of course, for a p orbital, L equals 1. Okay? So Herr Professor Pauli, who in later life was a big fat guy, I mean, just this big, rotund belly, unbelievable. Okay. So can you imagine this big, fat, old cigar-smoking guy talking about his principle? Okay, so we have 2 electrons that get to go in these 3 orbitals, right? Okay, so here are the possibilities. We can pair them up and put them there. Another possibility is we can pair them up and put them in the middle. And another possibility is we can pair them up here. But is that the only possibilities?
They don't have to be paired.
They don't have to be paired. Okay? So we can go up.
Wouldn't they not pair anyway? Just
But-
because it takes energy to pair, wouldn't they?
Well, hold on to that thought.
Okay.
Don't let that thought go, but we're going to do some other things. So let's do up, 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 down. Down, up, and down, down. You see there's 4 different choices that I can make there.
Mm-hmm.
And I can do it again, can't I? 1, 2, I'll do 4 more. Okay, are you ready? So these will be down, down, up, down, down, up, and down, down. I think I'm going to put double arrowheads on all these. Yeah. Wait, did I put them down when they should have been up.
You double down, down?
You doubling down?
Yeah, we can't. Okay, so we'll get arrows on all this. Submit. So there's another 4. And what's the final possibility? There's
One on the right, and all to the left.
one on the right, one on the left. That's exactly right. Okay, so there's up, up. There's up, down. There is down, up. And there is down, down. Now, how many possibilities have I written here? Well, we'll enumerate them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are 52 electrons into the p orbital, so this is p minus 1, p0, and p1, different values of m sub l. There are 15 different correct ways to do it. And by the way, let's show you something that you can't do. Up, down, and down, up. So up, down, and down, up are equal, and you only get to count one. Does that make sense? So with an actual paired set at an individual orbital, like these top three, 1, 2, and 3, it doesn't matter. That's considered just one choice, not two choices, okay? So we have 15 microstates. Now we're going to group them we're going to group into terms subsets of the total with the same energy. So Ed, you mentioned, hey, some are going to be lower in energy than others. That's exactly right. So out of these 15, would you expect that all of them have the same energy?
No.
No. So in a group of 15 girls, some are smart, some are dumb, some are fat, some are thin.
Some are beautiful.
Some are beautiful, some are dumb, some are ugly, you know. So these are not the same, but they're going to fall into 3 categories. You know, hot, blonde English majors. Oh, Phoebe, I'm sorry.
What are the chances of
I thought this was a gentleman's club. I forgot. You know?
Yeah, it's okay. She's not gonna watch.
She's not gonna ever see this.
She's too busy playing with kitties and stuff over there.
Yeah, she is. She just hasn't said a peep to me. Now, is she communicating with you any?
Oh, I see her on Snapchat.
Yeah.
She's enjoying the age difference out there, that's for sure. No, I'm just kidding.
All right. Now, let's do the following. We're going to sum up all the m sub l and m sub s values. For each of the 15 microstates.
Okay.
So we have 2 electrons, and they're both at an m sub l of -1. So what's the total m sub l? Got one with 1 unit of angular momentum at -1, and another with 1 angular momentum unit at -1.
So you got -2.
You've got -2. So what's this middle one? Number 2 state in our drawing.
Negative. I mean 0.
Exactly. Okay, since you almost didn't get that, what's this one?
2.
Okay. Now, do me the m sub s value. M sub s, you look at the arrows.
Sorry, I gotta take this one.
Spin, so what did they just even out? 0, 0, 0?
Yeah, 0, 0, because all those spins are paired, right?
Mm-hmm.
Okay. Now, we're going to have you do 4, 5, and 6.
Alright.
M sub L values are all going to be the
negative
same.
1,
Okay,
negative 1, negative 1, negative 1.
right? And M sub S
So wait,
is-
does M sub L values, it doesn't matter if the spin's up or down, it just matters what level.
That's right.
Okay.
So we have 4 negative 1 M sub L's. Okay, so what are the M sub S values for these
It's going to
4?
be identical but positives.
Okay,
Oh, sorry, I'm going way lower. Sorry. Yeah, those are going to be negative 1.
arrows up is positive.
So positive 2.
No, each spin is a half.
Oh, 1.
Okay, so 1. What's the next one?
1. No,
No, up
0.
down is 0.
0.
0.
Negative 1.
Negative 1. Okay, good. Oh, that call was timed perfectly.
Oh yeah. Just found out that I have been offered acceptance at Utah.
Big surprise. I figured that you had to take that call.
Yeah. Yeah, I was from Salt Lake City, so I figured might as well.
An 801 area code, right?
Nice,
Okay.
dude. Is that where you're going to go?
I'm feeling good about it. Yeah.
Cool.
So, when are you going to tell them?
Gonna take a couple weeks to make sure, but you know, I have until April 15th to decide. But like, I'm feeling really good about Utah, so.
Oh, good.
Yeah.
And of course, have the courtesy to tell the other schools.
Oh yeah.
You know, thank them because you might do a postdoc at one of them.
Right, yeah.
Right. So, yeah, big surprise on that.
Yeah. Yeah, it's just nice to know for sure.
Well, now you have the place you want.
Mhm.
That's great news. Congratulations.
Thank you.
Okay. So psi, we were assigning M sub L and M sub S values. We'll let you catch up to where we are, and we're going to have you do the next one, aren't we, Ed?
Yeah.
I mean, we should be smoking a cigar while he's doing that, don't you think? Or at least drinking a beer.
Oh, yeah.
I have caught up. Alright.
So you kind of see what happened here?
Yeah.
Okay, so give me the M sub L values of the next 4 from 8 till 11.
Alright. So we're gonna have 1. Wait, for 8 to 11, they're all gonna be 1.
Yes. M sub L's are 1, 8 to 11. 1, 1, 1, 1. And what are the M sub S values? Start with 8.
Let's see. Okay. So for number 8, it's gonna be negative 1.
Okay.
Wait,
2,
wait, those are both up.
and each one's worth a half.
Oh, okay, so that's 1.
Okay.
Oh, I wrote it backwards.
Yeah.
Okay. So that's gonna be 1. The next 2 are gonna be 0.
Okay.
And then the 4th one is gonna be negative 1.
Excelente. Okay, now, does everyone know how to do the last one? What's the M sub L value for the last set of 4?
It's gonna be 0.
That's right. What's the M sub S value?
It's gonna be 1, 0, 0, 1.
Mine's-
Negative 1, sorry.
Okay, there are M sub L and our M sub S values. How many microstates are we dealing with?
15.
15. And we'd like to know which terms or subsets of these are going to have the same energy. In other words, we could have 15 different energies, but in reality what happens is you get several clusters with different energies, and those are called terms. And we want to teach you how to get those terms because you'll need them for lab this afternoon. That's as good a reason as any to get the terms, right?
Definitely.
Okay. Now, here's how we get the terms. M sub s among these 15 microstates goes between -1 and +1, doesn't it? And what does M sub L go through?
-2 through +2.
Yeah. -2, -1, 0, 1, 2. M sub L. So you need to draw a little box with three columns and 5 rows. So isn't that 15? 3 times 5 is 15, right? Okay. Now what we want to do is find the number of terms that have a given M sub L and M sub S value. So how many 0 zeros do you see here? There's 1 here. There's 1 here. And there's 1 there. Are there any others?
Nope.
So the number of microstates with M sub L equals 0 and M sub S equals 0 is 3. And you put it right where it is, 0, 0. Okay. How many microstates have 1, 0? Okay, 1, 0 is 1 on the M sub L and 0 on the M sub S. So you're claiming there's a 2 right there, right? Okay, how many have -1, 0? -1, 0, there's 2 right there. Okay, how many have 0, let's see. How about 0 minus 1? How many of those do we have?
1.
Oh, wait a minute, I was on the wrong place, sorry. Okay, let's see. Oh, how many have 2, 0?
2, 0 is going to be one of those.
Okay. How many have -2, 0?
1.
One of those. You're starting to see some symmetry in this, aren't you? Okay. Now we've got a 0, 1 and a 0 minus 1. Where are those? M sub L equals 0, 1, and 0 minus 1 is there. And now I only have 4 left. I've got 1 minus 1, minus 1, minus, so I've got 1 minus 1, or minus 1, 1. Let's see, minus 1. M sub L is minus 1, and M sub S is 1. That's right there, right? And minus 1 is 1 there. And there's 1, 1, that's there. And there's 1 minus 1, there's 1 there. Now, if you've done this right, and you add all these numbers in here, so inside number of microstates with a given m sub L or m sub S and m sub S. So all these numbers should add up to what number?
15.
Do they?
Yep.
3 plus 3 on the outside, there's 6 on the outside, and 3 plus 3 plus 3, 6 plus 9 is 15. Perfect. And you can see the obvious symmetry of this problem vertically and horizontally, right? Okay. Now, it's funny that we talked about the trash man because we're about to use the trash compactor.
Cool.
Cool. I mean, you definitely want to be the trash man after this.
Can fulfill your dream style.
Yeah.
Did you ask the so the sanitation department called and offered you the dream job?
Yeah, I'm gonna have to turn all the schools down because, you know, I want to be a trash man.
All right.
When I was little, though, I'd like look out the window every day watching for the trash truck to come around. It was my energy.
No, that was your thing. Huh?
Yeah.
Okay.
Not anymore, though.
So this is what we were supposed to do, by the way, last Thursday.
Yeah.
And you can see why I was up to doing this. But at least you can sympathize with how bad I was feeling.
Yeah.
All right. So now we're going to do the trash compactor.
Trash man.
Okay. Now, you can either smash vertically, or you can smash horizontally. It doesn't matter which way you smash. You just choose a direction to smash. Now, you have the jaws of the trash compactor. What one do they hit? They hit m sub L equals 2 and m sub L equals minus 2, right? And as a result of that, something happens. Okay. Here's what you're left with. Okay, do you see that I removed 5 microstates?
Why did that happen?
Yeah.
Okay,
I don't even know.
the first thing the jaws of the trash compactor hit, you take away 1 microstate from every one of those.
Okay.
And since these were sticking out, I hit those first, and you take the whole column that it hit. Now, we have it. Now, the microstates have m sub L that goes between 2 and minus 2, they have m sub s equals 0. Now, if m l equal, 2. If m sub s equals 0, what does s equal?
1/2.
So there's no range in m sub s, therefore s has to be 0. This one goes V2 plus. So these 5 term microstates are characterized by a total orbital angular momentum L of 2. The quantum number is 2. And spin quantum number is 0.
Okay, wait, now what does that correspond to?
This says there are 5 microstates
That you removed?
that have the same energy,
Okay.
and that energy can be specified by giving the total angular momentum L equals 2 and the total spin angular momentum S equals 0. So we have it. This defines a term called superscript 2s plus 1 to the L. This is called a term symbol. Okay. So for L, if L takes on the values 0, 1, 2, 3, 4, 5, 6, there's a letter value that goes with that. S for 0, capital P for 1, capital D for 2, F, capital F for 3, G for 4, H for 5, I for 6, and so on. So in final form, this term symbol is 2, and what's our S quantum number? 0. 2 times 0 plus 1 divided by, and our L happens to be 2, so this is a D term. So it's 2 times 0 plus 1 to the D, or this was a singlet D term. And there are 5 microstates embedded in that term, and they all have the same energy. Okay.
I don't know what that meant.
Yeah.
I'm not trying to just pull out random crap, just trying to make something up.
This is directed crap, like the monkeys throw at the
Yeah.
like the gorillas throw at the zoo patrons.
I get what you're doing. I get when you're talking and you're moving to the next step, but I don't understand the overall picture. What do you mean you're smashing what vertically?
Yeah.
Okay, this is trash. I'm smashing the trash vertically. And when I hit these, I remove
all
one.
microstates.
Yeah.
Drop 1.
Now, this is just a mathematical trick to get the right microstates. There's nothing physical.
Got you.
I'm not doing any chemistry or spectroscopy.
That's what
I'm doing a mathematical trick.
That's what I'm wondering. So what do you mean getting the microstates? I know you're doing a trick, but a trick for what?
I've got 15 microstates. I want to know how they rank energetically.
Okay.
So you're trying to...
So then, by this method, I classify them into common values of capital L and capital S. And once I get their capital L and capital S value, I can tell you where they sit
Okay.
energetically. That's Hund's rules. Have you ever heard of Hund's rules from general chemistry, maybe? Let me put the trash compactor on again. Now, it doesn't matter here, we can smash the trash horizontally and vertically, we'll get the same result. But I'm gonna do it horizontally because I did it vertically the last time. By the way, it won't matter which one you start with. Do it any order you want, you'll get the same thing.
So you have to smash it vertically and horizontally? You gotta...
You know, you might be able to do it all one direction to get it. Okay.
It's more fun to do one of each.
Yeah, so now I'm going to smash it horizontally, and I'm going to remove one microstate from every place I've smashed it horizontally. Okay, -2, -1, 0, 1, 2, -1, 0, 1, m sub s on top, m sub l on the bottom. Now, if I smash this horizontally, it runs into 3 rows all at once. So I've got to remove 9 microstates out of there. And what's left after that is just a 1 right there. So I smashed horizontally. This sounds like a mosh pit at a rock concert.
Yeah.
Okay, so I smashed horizontally, okay, and I removed 9 microstates. Now, it turns out that the m sub l values of what I removed were between 1 and -1. That implies that L equals what? If m sub L goes between 1 and -1, L has to equal 1. Okay? M sub S is also going between 1 and -1. Therefore, S also equals 1. Therefore, 2 times 1 plus 1 to the 1, and for L equals 1, that's a P. This is a triplet P. That is the triplet P term. Okay, so right now we have a singlet D term and with 5 microstates in it, and a triplet P term with 9 microstates in it. And lo and behold, if we smash on this, we get. So let's just do that. Smash vertically. It wouldn't matter whether it was horizontal or vertical. I'm going to get something with m sub L and m sub S. Guess what? How many microstates did I remove on that last step? 1. Remove 1 microstate. And for this one, m sub S equals 0 and m sub L equals 0. That is a singlet S. So we have the 15 microstates, therefore, in carbon, we can divide into 3 terms. The singlet S has 1 microstate. The triplet P has 9 microstates. and the singlet D has 1 microstate. Oh, excuse me, singlet D has 5 microstates. And what is 5 plus 9 plus 1?
15.
15. So we've taken our 15 microstates and we've grouped them into 3 different energy levels. That 9 of them have this energy, 5 of them have this energy, and 1 of them have this energy. Okay. Now, which order do you think the energies are in? So if energy is going this way, which one of these 3 do you think is lowest?
S.
Yeah,
Okay.
Go to S.
You're totally wrong. Triplet P is the lowest. Okay, so the triplet P is the lowest. Now let's see. Just let me look real quickly and see if they say anything about this. They don't do a lot. They don't do. Yeah, they don't really. Okay. They don't really do a lot here. Okay. So the triplet P is lowest. There's a set of rules due to this guy named Hund. Say the term with the highest spin has the lowest energy.
Yep.
And then if 2 terms have the same spin,
For degenerate.
our singlet D and our singlet S, the one with the highest orbital angular momentum has the lower energy. So a D state is next, so singlet D is next. And the one with the lowest L and the lowest S is high, so the singlet S is highest. So now we've learned the whole reason why we went through this hour of torture. We can now classify atomic spectra.
Okay, wait, why was the S the lowest or highest energy?
Because it had the lowest spin and orbital angular momentum.
Okay, so like you add those up, or?
Right, well, you've already done it.
Yeah.
An s orbital has 0 orbital angular momentum,
Oh, okay.
and it has 0 spin angular momentum in singlet S. Now, I'll talk more about Hund's rules in our next meeting, okay? But now we want to take a brief break, and we'll go down to the lab, and we'll put all this into practice.